Okay, so in this module, we'll talk about sampling or optimization error in RL. So our goal here is to answer the questions of the form of what you see here, which is how does the error in training translate to error in, let's say, the value function or the Q function that you end up learning. We'll analyze these errors, optimization and sampling errors, in two settings. The first is a setting of a generative model that we saw in the first module. The second is the fitted Q iteration setting, which we saw earlier in the offline reinforcement learning lecture, as well as in the deep Q learning lecture. And what kind of results do we want here? So we are aiming for results that show something like what you see here on the slide. So we want to be able to intuitively say that if the learned dynamics model or is close enough to the actual dynamics model, the learned dynamics model is p hat and the actual dynamics model is p. If their L1 distance is small enough, then we want to be able to say that the difference between the learned Q function, where the Q function is learned by planning under this learned dynamics model, is close enough to the actual Q function. So Q hat minus Q at all state action pairs, which is indicated by the infinity norm, the infinity subscript that you see there, that difference is smaller than some delta. And delta is a function of epsilon, and we need to derive what that function looks like. So we want to be able to say something like this. Similarly, for the fitted Q iteration setting, we want to say that if the TD error or the Bellman error that you minimize during fitted Q iteration, which is QSA minus sort of an empirical Bellman operator of QSA, and I'll describe what the empirical Bellman operator means in a second. But if that difference, or if the training objective is small enough, meaning that if you do a good job at training, then your Q function that you get out of it should also be a good Q function, meaning that the infinity norm between Q hat and Q should be small enough. Now, what is this empirical Bellman operator? So this empirical Bellman operator is essentially the same as the original Bellman operator, except that the reward function and the dynamics model are estimated using samples. So sort of p hat, so you use p hat in the expectation over the next state, and you observe r hat, which is the, let's say you saw a state action pair n times, then you're averaging over the different reward values you got. Now, when you have deterministic reward, which means that the reward function is not a stochastic function, then r hat is equal to r, which is typically the case. In theory, although the reward function can be stochastic, and in that case, r hat may not be equal to the mean reward or the actual reward. And so, just as I said, empirical Bellman operator is constructed using transition samples observed by sampling the MDP, which is what T hat refers to. So our goal is to be able to come up with results of this form, and most of our analysis will really talk about how, given an epsilon, so given a notion of training error, so epsilon is the training error because you can fit p hat against p, you can fit q against t hat q. Given that notion, what does delta really look like in terms of epsilon? And then we'll talk about whether delta is super large than epsilon, or is it a constant multiplier of epsilon, etc. And that's sort of the analysis we are aiming for. So the first part, let's start with sampling error when you have a generative model assumption. So just to recall, what that means is we estimate p hat of s prime given sa using the number of times, using ratios of counts, where n is the number of times you ended up querying the true dynamics for s comma a, and sa, the hash s s prime is the number of times you actually observed s prime coming out of your true dynamics model as the sample. And your algorithm here is just that for a given policy pi, so we are not doing any policy learning, we are sort of doing policy evaluation here. So for a given policy pi, we plan under the dynamics model to obtain the Q function Q hat pi, which is our estimated Q function. And for this analysis, let's assume that the reward function is known to you. So R is known exactly, RSA is known exactly. It's a small step to extend the analysis to the unknown reward functions, where you also estimate the reward function using some kind of averaging, and that is sort of left as an exercise for you. But the analysis basically remains the same in that scenario as well. So okay, so let's get started with the proof, and we'll go through this proof again in the class if there are any doubts or if there's any questions, if something is unclear. So the first step here is we would talk about, so imagine this scenario when, let's say you know the exact dynamics model. So we know exactly what the MDP's dynamics model is. Then we know that if we also know the reward function, which is an assumption here, the the planning under this exact dynamics model is going to give me the exact q function q pi. So there's no reason to expect that q pi will not be equal to, or q hat pi will not be equal to q pi if I knew p hat was equal to p. So the only reason why we expect this difference is because p hat is not equal to p. So how different is p hat from p is the first step that we are going to do. What is the way to do it? We'll use concentration inequalities that we saw in preliminaries. The reason why we'd use them is because here really what we're doing is we're sampling state action, or we are sampling S primes for a given SA, and we're observing n samples and using that, and we're using that to estimate the empirical model. So there's sampling involved, and so concentration inequalities are the way to go. So using sort of the second lemma that we had there on the preliminary slide, where we talked about concentration for discrete distributions, we can show that the L1 norm of the difference between p and p hat is bounded by some constant times square root of the size of the state space times log 1 over delta by m. And this statement holds true with probability greater than or equal to 1 minus delta. So if you put delta to be small, this holds true with a high enough probability. And what is m? M is the number of samples used to estimate p of S prime given SA, meaning that m is the number of times you queried SNA through your true dynamics model. For notation sake, n is equal to m in this setup. What this tells us, to summarize, is that the empirical dynamics model and the true dynamics model are actually close. Okay, the second step now is we need to talk about how exactly the dynamics model affects the Q function, because so far what we've shown is dynamics models are closed. So if we know that the Q function is sort of, or the change in the Q function due to change in the dynamics is depends on how much the dynamics changed, then we can simply use the resulting concentration bound that we saw on this slide into that expression to obtain a bound on how the Q function changes. So in this section, we'll talk about how the dynamics model affects the Q function. So before going down into how exactly it affects it, let's look at a slightly different representation for the Q function. So it's a representation that is a vector representation of the Q function. And now instead of talking about QSA, we'll deal with vectors of QSA values. So you basically take the Q function for each state action pair, arrange that into a vector, and that's the vector we'll talk about. So we know that the value function is basically the Q function evaluated at, so value function of a state S is the Q function of the same policy as the state S and action drawn from the policy pi. So that can be written in the first line. And the Q function satisfies this Bellman equation that is not the Bellman optimality equation, but the Bellman equation for consistency for a given policy pi. Now let's do this. Let's define P pi as a matrix, which is a matrix of size SA cross SA. So state size of the state space cross size of the action space. That's the row dimension. The column dimension is also mod S cross mod A, same value. And what we'll put inside this matrix is we'll populate this matrix at a particular row location SA and a column location S prime A prime as equal to the dynamics probability of transitioning from SA to S prime times the probability of taking action A prime at state S prime. So that's the value we populate this matrix with. Now I claim that it should be that we can write the Q function in vector form. So Q function now, Q pi refers to a vector which has entries Q pi SA for different state action pairs. I claim that we can write this as, we can rewrite the Bellman equation as Q pi equals R, where R is again this vector of size S cross S times A, plus gamma times the transition dynamics, which is a matrix which maps SA inputs, which is state comma action, to the next state S prime. So that's the P matrix, times V pi, which is a vector of size S. So that's the Bellman equation. Now, if you want to replace V pi with Q pi, we can take a step further and use this matrix P pi that we defined earlier to write down Q pi is equal to R plus gamma P pi Q pi, where P pi now is an SA by SA matrix. Q pi is an SA sized vector, so you see that the matrix multiplication also works out. So with this Bellman equation, with this consistency equation in matrix form, in vector and matrix form, what you can do now is you can take the gamma P pi Q pi term to the left, subtract it out there, you'll get I minus gamma p pi, and take and multiply by the inverse of this matrix to obtain an expression for q pi, which you see on the slide. So q pi is equal to I minus gamma p pi inverse times r. Now, why is this matrix invertible? This matrix is invertible because gamma p pi is in some sense smaller than 1, because p pi consists of probabilities. As you see, gamma is smaller than 1, which means in a discrete setting, this matrix is lesser than gamma, which is smaller than 1. So it is intuitively, that's the reason why it is invertible. But for a formal proof, I would encourage you to work it out yourselves as to why this matrix is invertible. So you can write down the Q function as this matrix I minus gamma p pi inverse times the vector of rewards. And if you see this now, the Q function really depends on the dynamics model via somewhat of a nonlinear transformation, because dynamics model probabilities are captured in P, and it's really a nonlinear transformation in there. So now that we know this this vector form or this vector matrix form for the Q function, we can use this to compute how our Q function would change if my dynamics changes from P to P hat. So I've written down the result on the slide, on the right part of the slide, which says Q pi minus Q hat pi is equal to the I minus gamma P hat pi inverse matrix times something that resembles P minus P hat, which is the difference between the change in dynamics. So if you put P equals P hat, you will find that this right-hand side is 0, implying which is consistent with our intuition that the dynamics model doesn't change. You should be able to estimate the true Q function. So how can we derive this? So I'll also probably go through this in the class. So if there are some doubts, I can answer there. But really, the intuition here is let's follow step by step what we're doing here. So q pi minus q hat pi can be written as the q pi in vector form minus q hat pi in vector form. So that's directly using the result on the left part of the slide. Now, what you can do is you can, by a little bit of manipulation, you can take out I minus gamma p hat pi inverse outside. So you can take that term outside. And you'll find that you'll be left with two terms that look very similar to each other, except that they have p hat pi and p pi respectively. And the outside multiplier will now become q pi. By doing a bit of manipulation where you cancel out the identity matrices inside the term that is that looks like it can get simplified, you'll find that you will end up with an answer that looks like gamma I minus gamma p hat pi inverse times the difference of the transition matrix times the value function of the policy. You should work it out if there's any if it's not clear to you. But that's the way we get this expression, by just sort of algebraic manipulation on this vector representation of the Q function. Now, there was a little bit of a glitch here, but okay. So the goal here is you express the Q function in vector form, and you are able to obtain the difference between the Q function values in a closed form sense. Okay. So now that we know how the Q function changes with respect to change in the dynamics model, we need to now use the fact that we were able to bound the dynamics model a few slides back using concentration inequalities, as you see here, to bound the difference between the Q function. And just as a reminder, what we really want is we want an infinity norm bound on the difference between the Q functions. So we now have the vector difference, we want the infinity norm of the difference. Yeah, so how can we do it? So we start with this equation that we saw earlier on the last slide, where we proved that q pi minus q hat pi depends on this I minus gamma p hat pi inverse matrix times the change in the dynamics function, and this is still a vector, times the value function. Now what we want really is we want to compute the infinity norm of this matrix, of this vector of q pi minus q hat pi, which means that we need to compute the infinity norm of a quantity on the right hand side of this equation. And that quantity looks a lot like the infinity norm of I minus gamma p pi inverse times some vector v. So what this statement on the slide says is it tries to bound the infinity norm of such quantities that resemble I minus gamma p pi inverse times some vector v, which is what is written on the slide. How can we show this? You can show that you can show this result by using a simple inequalities. So let's define W to be I minus gamma p pi inverse times V, which is basically the quantity whose infinity norm we are interested in bounding. Now I claim that we can write it in this form, where we say that the value, the vector V is equal to I minus gamma p pi W. Just by multiplying I minus gamma p pi on both sides, you can recover that. So the infinity norm of V is equal to the infinity norm of I minus gamma p pi times W, which by triangle inequality is greater than the infinity norm of W minus gamma times the infinity norm of p pi W, because triangle inequality says norm of A minus B is more than norm of A minus norm of B. And finally, we note that p pi, because it's a matrix of probabilities, every entry is less than 1, you can show that that this p pi w's infinity norm is going to be smaller than the infinity norm of w in itself. And because there is a subtraction, you can show that this quantity is more than equal to w infinity minus gamma times w infinity. By just rearranging terms and by taking 1 minus gamma out common, you would find that you can say that w infinity is less than v infinity by 1 minus gamma, which basically proves our result here, because I minus gamma p pi inverse v is equal to w. So what have we shown here? So we have shown that if you were to bound the right hand side of the q of the difference between q values, or basically that term also consists of I minus gamma p pi inverse like terms. So what we can do now is we can simply put an additional 1 over 1 minus gamma and only look at the infinity norm of the vector that is multiplied to I minus gamma p hat pi inverse, which is equal to the infinity norm of p minus p hat times v pi, which you see on the last line of this slide. Okay, so now we finally complete the proof, and this last bit in the proof is basically a little bit of algebraic manipulation to really just use the L1 norm between the dynamics models, between the learned and the true dynamics model, which we proved at the very beginning of this proof. Basically, we want to get into it. Basically, what we want to do is we want to convert the right hand side of the last inequality, which you see in this slide, into a form that allows us to use that result and directly plug it in here. So this is the result directly copied from the last slide, where we showed that I minus gamma p hat pi inverse can be removed when you talk about infinity norm by adding 1 over 1 minus gamma. Now, what we are doing next is we are saying that infinity norm, what is the meaning of the infinity norm? The infinity norm is basically, so infinity norm of V is the maximum, is equal to the absolute value, or is equal to the maximum possible absolute value of any element of that vector. So it's basically max over Vi, the absolute value of Vi. So what we can do now is we can say that if you were to bound the maximum element, the maximum value of a product of p minus p hat and v pi, we might as well just bound the product of the maximum elements, right? Because this guy the maximum value of a product is less than equal to product of a maximum value intuitively, right? So what you can do, but that's not exactly the case here, because P is not a vector, it's a dynamics. It's a matrix. So what it ends up happening is it ends up giving you this inequality, which you see on the screen, which says that gamma over 1 minus gamma gets copied. The max over SA of the L1 norm comes in, because P is a matrix, and the infinity norm of V pi comes in, which is V pi infinity that you see there. So this is what the expression comes out to be. Now what we can do is we can use the fact that let's say the maximum reward of the system is bounded, which means that R max, there exists a limit, which is, let's call it R max, such that the reward vector R of SA at each state is going to be less than R max. And what we can do is, without loss of generality, we can assume R max is equal to 1 for now, because R max really is just a constant that would appear anyways. We might as well assume that that is 1, and that doesn't really change anything. Then the value function of a policy pi is basically the sum of discounted rewards over the entire horizon, right? That's the definition when you follow policy pi. So when the maximum reward is 1, what's the maximum value of the value function? The maximum value of the value function can be essentially the effective horizon length, because you can assume that in the worst case you see a reward of 1 1, or the R max reward at each step, and there are h many steps, or 1 over 1 minus gamma many effective steps in your system. So what is the maximum value of the value function? It is 1 over 1 minus gamma. And if you see the transformation between the second line and the third line, the real difference is that there is another factor of 1 over 1 minus gamma multiplied in the third equation, and the v pi infinity is gone. So where did that factor come from? It came from the fact that the value function in its infinity norm is bounded by 1 over 1 minus gamma times a constant, that is R max, which is assumed to be 1. So now we are at a situation where we know that the infinity norm of the difference between q values is less than some constant, which is gamma over 1 minus gamma square, times the L1 norm of the divergence between the dynamics models, right? So what we can do now is we can use the previous relation that we derived via concentration inequalities to basically say that the difference between q values in infinity norm sense is bounded by the same constant that you had from before times some constant c, which comes from the previous equation. We need not know what c exactly is, because we only care about sort of the asymptotic behavior and not really constants, and times the expression directly taken from p minus p hat. And if you want to talk about, if you want to say that you want to have exactly, let's say, epsilon error in q pi minus q hat pi, you can compute how many samples m you need to get this error. And how you do that, you would say that the right-hand side should be equal to epsilon that you care about, and you solve for m using this equation. So right-hand side equals epsilon is your equation. You want to solve for m. You can take a square and take m to the other side, divide by the epsilon square that you get, and you will get an expression. So what that tells us is if you want epsilon error in your q function, you need to have m many samples, which you see as a result of that. So to summarize, what we showed here was a bound that says that approximation or number of samples that you took for finding your approximate dynamics model affects the q function in this functional way. And if you want to derive how many minimum samples you need to be able to learn an epsilon accurate q function, you can compute that by equating the right hand side to epsilon. What other takeaways does it tell us? So the first takeaway it tells us is that a small error in estimating the dynamics model, meaning that if you had error that looks like if you estimated p hat minus p up to this error, then that small error gets multiplied by a large constant that is gamma over 1 minus gamma square. Now, a small error in the dynamics probability does imply a small error in the q function. It's just that the notions or the magnitudes of small are far apart, because you're multiplying by gamma over 1 minus gamma square. And 1 over 1 minus gamma square, let's say gamma is 0.99, then 1 over 1 minus gamma square is 1 over 1 minus 0.99 square, which is 1 over 0.01 square, which is super large. So you magnify errors, but a small error nevertheless corresponds to a small error in the q function. Finally, the more samples we collect, that is, let's say if samples are not free, if samples are free, meaning that we can collect as much data as we want, then we can estimate the true q function because of concentration. Okay, so for the next part, what we'll do is we'll talk about how does optimization error or sampling error manifest in model-free methods such as fitted Q iteration.